In estimating the Leisen Reimer tree here, we note that for the call option and for the put, which we'll look at in a moment, the region, the zero region in the respective call and put option trees are fixed. They don't change. So as we adjust parameter values here for the option, let's say even change the volatility, the tree itself will change in the values of the tree, but the zero region remains intact. Okay, so when we go back and change our value, parameter inputs, back to 0.3 again, the value of the option remains, can change, but the zero region is still intact. Okay, so taking that into account then in terms of coding, when we go through the loop here for the call option, I break the snippet of code down into, for the truncated dynamic Leisen Reimer binomial tree here. The intrinsic value is estimated as before, so no change in terms of the intrinsic value. And the backward recursion, again, the same basic technique. If we look at the code here in terms of the European option or the American option, when we compare that against just the dynamic tree, which doesn't exclude, same basic code is being applied. The major difference that occurs here occurs in terms of the relative values of the j and I. So ideally what I want to achieve is to remove the zero region, and that would mean when I start my estimation, I go from this value of 8, in the backward recursion at least, I start from this value of, well, in that instance, 7. Okay, so to take a look at that, how we might engineer that, in this instance here I say j starts off at being n minus 1, and we continue to j is equal to n plus 1 divided by 2. Now n here in a 15-step tree is 15, right? And we're in the penultimate node, so that is, or the penultimate column, so that's 14, n minus 1 is 14. And then in terms of how far do we go back? We don't go back to 0 as we had done before. In the previous instance, we just went straight back to 0, continued that sequencing of j's back directly to 0. Here we go back to n plus 1 divided by 2. So n, 15 plus 1, 16 divided by 2 is 8. And what we're trying to do is go back here to 8. So we continue the type of estimation that we do, but we only go back as 8, and that's where the zero region ends, and we'll see why in a moment, why we're progressing it like this. Okay, next part of the estimation then is to select the I, and I here is obtained by taking the j, which in this instance is n minus 1, which would have been 14. So 14 minus n minus 1 again divided by 2 is 7. So 14 minus 7, starting off here is, we don't start at I equal to 0 as we had done before, I equal to 0. We start off at I equal to 7. Okay, so let's take a look at that. 7, what does that mean? It means we don't start here at I equal to 0. We actually start off here at I equal to 7, and then we go from that I equal to 7 to I equal to 8, all the way I equal to j. Remember that j is equal to n minus 1. Okay, so we go all the way from I equal to 7 up to and including I equal to j, where j is equal to n minus 1, so starting at the penultimate column. So we go to I equal to 14. Then we go, and then we run these valuations like what we've done before. So no change here in terms of the backward recursion, estimating the European or American option. Then we go back to the loop, and in that instance, the second time through, now j becomes, we reduce j by 1, so j is n minus 2, so that's 13. And we come down to I equal to 13 minus 7, which is 6. Okay, to see that, go back into the tree. So we go back to n minus 1 before, now it's n minus 2. And because it's n minus 2, we want to start off not at 7, we want to start off at 6 and run the valuation, perform the backward recursion starting from this point going up. Can we show up to 13? Can we engineer 6 here? The way we engineer 6 in terms of our estimation is we say j is equal to n minus 2. As when we go to the second loop, we've reduced it by 1, n minus 2, so that's equal to 13. 13 minus n minus 1, well, n minus 1 is 14 divided by 2. 14 divided by 2 is 7. 13 minus 7 equal to 6. So we start off at I equal to 6. Again, the logic here for generating I equal to 6 is we want to start from here. We don't want the zeros. We want to exclude the zeros, and we want to run the valuation sequentially. If we go back again, it becomes n minus 3. That instance, n is equal to 12. If j is equal to 12, then if j is equal to 12, 12 minus 7 is equal to 5. So I starts off at 5. Okay, and is that where we want to be? Yes, we want to be at when j is equal to 12, we want to start off at 5. When j is equal to 13, we want to start off at 6. When j is equal to 7, we want to start up. When j is equal to n minus 1, we want to start off at here I starting at 7. Okay, so we're excluding the zeros by imposing this type of code. Now once we get as far as that point, then we want to revert back to not excluding zeros. So at that point, once we cross over here to 7, we want to run that as usual. This snippet of code here is if it's only relevant if the option is a put. That's how we truncate the put option. In this instance here, once we've run z equal to -1, we estimate up until this point here. Then we start off here. How do we start off at that point? We come down to, for j equal to n plus 1 divided by 2, so n plus 1 is 16 in a 15-step tree, divided by 2 is 8, minus 1 is 7. So we start off at 7, and then we go from at 7, when j is equal to 7, I starts off valuing using the backward recursion, starts off at 0 and goes up to the relevant j in that instance. And the code has remained the same here as we observe here. Okay, so basically that has let's do a trial run here of this. If we change the value of n to 15 and take these parameter values and run the estimation, we can see the value here is 821.88, 821.88. If we take the same parameter values here using the code Leisen Reimer code from Espen Hogue, we also, for the American option, we get 821.88 in a 15-step tree, and the parameter inputs, the stock price, the exercise, the time period, risk rate, B here denotes R negative Q. So If b is equal to 0, it means q is equal to 7%. So r is equal to 7, q is equal to 7, v is equal to 30%, 15 step 3, 82188, and the result that we obtained in terms of the C++ code is 82188. Okay, so that's mildly reassuring. We could do another little check here against Leisen Reimer. We have keep in mind that we're looking at the European and American. Because the dividend is 0, the European options values will be equal to the American option value. So with exercise 100, stock price 100, risk-free rate 7, dividend, no dividend, volatility 30%, time period 6 months for 25 step 3, the value that we get is 10.13316. Okay, so let's go back and just test our model here. Again, is it a call or a put? I think we said it was a put, a call, and we want to run for 25 steps. Delete 25 and let's run. And just change our value to 0 for a dividend. And the value we get here in terms of the American call option is 10.1316, which is shared here in terms of Leisen Reimer. So 10.1316, same result. Okay, what about for the American put option? Then we should get 7029 for those parameters. So I'll go back in, and with this truncated code, again, run it for the call, but I'm going to run it now for the put. And for the put option, let's change C to P, delete and P, and run. For the 25 step 3, taking those parameters, we get 70285, 70285. So let's just compare that against the American put 702981 for 702858. Okay, for the Leisen Reimer tree. Okay, just to observe a little bit the structure of the put option for a moment. The put option is a bit different here in terms of the way we estimate. For the call option, z is equal to 1. We have this. Otherwise, if the z is equal to -1, that implies that our put we had put down as being that the option is a put. So for z equal to -1, we have a put. And then in terms of how we organize the loop here, we start off j is equal to n-1, and we go back to 8. So we saw that before, no difference from what we had here. But the second part is different. I goes from 0 to n-1, n is 15, -1 is 14, divided by 2. So I keeps just going to 7. And to see why that works, just come back into our tree here for a moment for the Leisen Reimer put option. And I've set up the put option here in the following manual tree. And for the Leisen Reimer put option, we find the value will go, when we're doing our backward recursion to exclude the 0 region, I should go from 0 to 7, 0 to 7, 0 to 7. So it's actually fixed. The value is not changing in terms of like the call option. The value of I actually in this instance is fixed, and we just want to run it up to 7, and we do that up until we get to 8, and then once we cross to 8, then it reverts back. Okay, to see that. So once we perform the loop up until we get to 8, n plus 1 in a 15 step tree, n plus 1 is 16 divided by 2 is 8. So the value of I, once we get up to j equal to 8, up and including, once we pass back to this 8, I will remain fixed at n-1 is 14 divided by 2 is 7. So it's fixed at 7. And that allows us to truncate the zeros